Okay, so we've made our linear models, as you can see in our spreadsheet. Oop, right there. We've made our linear models. There's a model there, there's a model there, and we didn't make one here when I didn't say why. So if you use those models, how accurate are they, if at all, and are they actually a valid model? That's what we need to know. So the last step is to figure out the significance of the correlation coefficient, right, which will tell you if the model is good. So the R is the correlation coefficient. So we have to do a t-test. So this is our observed t, and then we'll figure out the hypothetical t from there. So let's go to our spreadsheet, and we'll say, for argument's sakes, that the observed t is lowercase, and the hypothetical we'll say is uppercase t. We'll compare those two, just for argument's sake. They don't necessarily, it could both be lowercase t, but kind of a comparison. So we'll copy those. Now let's copy this first. Copy, paste, um, paste, and then we'll copy these. Copy, paste, paste. Okay. So our observed t, or t value, is the r value. So we have to click on r times the square root, parentheses. So n minus 2. So 1, 2, 3, 4, 5, 6 minus 2 is 4. Divided by, this is where the mistake comes in, another set of parentheses for 1 minus r to the second, and then close paren twice, because you need parentheses for that whole denominator. Otherwise, it's only going to divide by 1, which is not going to change anything, obviously. It's divided by the whole denominator. Okay, so there is our observed t value. Okay, let's do that all the way through. So we'll go to the next one. Equals the r times the square root, and this is 7, I think. 1, 2, 3, 4, 5, 6, 7. So minus 2 is 5, divided by parentheses 1 minus r to the second. Close paren twice. I think if you forget the second paren, I think it auto-fills it for you, to be honest with you, but that's fine. Okay, then our final r value observed equals the r times the square root, parentheses, I don't remember what this was, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Minus 2 is 8, divided by parentheses 1 minus r to the second, close paren twice. There is that. Okay, so let's talk about what you're trying to compare it to. So the hypothesis test, which we're not going to completely carry out because we don't care about discussing the outcome of the hypothesis test, which is whether it passes or fails. Do we use it or not? That's all we really care about. So we're not going to go through the full formal process. And this can be R, or this. This is not actually a P; it's a Greek letter, but either it's equal or it's not, basically. So you always assume there is no correlation, right? Basically, there is no relationship, therefore the model is invalid. You always assume the model is invalid unless proven otherwise, basically. So therefore, our equation is valid because the correlation coefficient is valid. And we'll use alpha 5% to start with. Okay, so basically we want to do a two-tailed test. Okay, so we need to find our observed t value, right? And then compare that to our hypothetical, or t value, which we're going to call uppercase t. So either that t is going to be over here or over here if it's significant. If it's not significant, it's in here. So just like any other t-test. So it's a two-tailed t-test because it could be a positive or a negative linear model. We're not sure. It doesn't matter. We'll count for both by doing a two-tail. We can modify it by doing the way we used to do in the past, but that's fine. Okay, so I'm going to go back to our spreadsheet, and we're going to do equals, remind myself. Actually, if I think about it, I can actually just start typing and it'll give me the options. So t dot inverse, oh, there it is, it pops up right away. Oops, 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 oops. So it wants the, tell me what it does, so I want to click on that, right? And then I want to put in the 0.05, which means it's going to put 0.025 on either end, right? Comma, degrees of freedom. So I have 6 values here, so it's 6 minus 2. So it's a minus 2 in this scenario. You can read the reasons why in the book, but it's not a minus 1, it's a minus 2 for this two-tailed test. So there's this one here. So I got a 2.77, so that's our theoretical. Okay, so that's actually plus or minus because it's a two-tail. Okay, so it's basically doing 0.025 on either end. So 277. So if you look back at my notes, I've already have it out. Okay, so this area here, right, is 0.025, and this area here is 0.025, right? So it took care of that basically, and this is our t-value predicted, you know what I'm saying, the modeled, and this is what we had for our observed basically, which would mean it was in the shaded region, right? Which means it was significant enough, therefore, right, our R value, correlation coefficient, is good enough. If it was in here, not good enough, right? So same thing as, so you always assume the null hypothesis is there's no relationship between x and y. So if you find enough evidence in either this region or this region of the two-tail, that means your correlation coefficient is good, which means your linear model is good. So now I can do these predictors. So let's say I have $150,000 in sales. What is the revenue? Okay, let's go to our spreadsheet. So we'll go over to here actually, equals, so the equation is a plus bx. So a plus b times 15, right? Because remember, it's, if I remember correctly, it's 150,000, but it's in tens of thousands. So we only put this, right? So go back to my spreadsheet, and I get 1.988 in billions of dollars, correct? That's the revenue. Okay. So the other question says, what is the predicted revenue for 500,000? You cannot do that one. You're like, why? The model works, right? We already proved that the model works. Yes, but if you look at the data, right? Let's go back to the data. 500,000, right? Because this is 15 is 150,000. That's 200,000. That's 63. Oh, let's change it actually to, let's change it to 1 million. Let's change it to 1 million, and I'll get what I want here. Okay, 1 million in sales, right? Why can't I do it? I was just looking here, and there's actually a 63 here, so that would make it in there. So if I do 1 million, that's beyond all these values, isn't it? So, can you always use the equation? No, even if it's a valid equation, because 1 million is beyond all of these. So 630,000 looks like to be the highest. So why would that be? If I go back to my list of problems back here, it's extrapolation. So if I try to do 1 million, that is beyond the data set, right? So if you're way too low or way too high than what the actual data set is showing you, that's extrapolation. You're trying to extrapolate answers from data that doesn't actually show you that range of answers, basically. So that's an invalid answer. You cannot answer. So this one you can answer, which we did, right? We got $1.98 billion. That's the estimate, right? Is it perfect? No, because at some point, you know, it's not going to be in there. And we were doing, what, 15, so somewhere in there, right? So that's about right, 1.98. That's about what it says, right? Because there's 2, so it's almost 2, isn't it? But if you go over here, 63 is the highest, so 1 million's over here. You're beyond the data set. You can't do that. Okay, so the next one, absences. Let's go to here. So now we want to do it for 0.01 for absences. Okay, and then predict 10 absences. That's fine. All right, so let's go to our spreadsheet. So I want to go to do t.inverse two-tail, right? We want the 0.01. So, whoops, crap, I hit the enter key by accident. 0.01, comma, degrees of freedom is minus 2. So 1, 2, 3, 4, 5, 6, 7. So 7 minus 2. Close paren. Let's get rid of that extra 1 there. Okay. So essentially, if you do the picture, which you don't need to, you can just figure it out. So you assume there's no relationship. So basically, 4.03 negative, 4.03 positive, and we got this right here, which is over here, right? Which means I made it to the significant region, which tells us that the correlation coefficient is significant, which means our model is valid for the range of data that we have. We can use it, correct? We're good. Okay, so what did the question ask? What if we have 10 absences? Okay, so we'll say prediction. Over here, we'll say the same thing, prediction, because your prediction, right? Because again, that's why you had the little y hat there, because it's prediction, not exact. So equals a plus b times, and it's 10 absences, right? So x is the input, which is 10 here. So that is your percent grade, right? Final grade, I believe, right? Okay. So, and 10 is that within the range? Yeah, 10's within that range. So that's a valid prediction. If I look at my graph, 10 absences, I go up to there, it's 60 something, right? That's about where it is. Does that kind of make sense? All right, let's go to the last one, the pupil-teacher ratio, right? And the question says to do for 10 alpha, that's fine. Okay, so equals t dot inverse 2. Okay, so we're going to do, it was 10, right? Comma, what's 11? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I thought this was 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I guess it's 10. 10 minus 2. Okay. Oh, wait a minute. That's not going to work, is it? Come on. So now I have 1.85 and negative 1.85, right, for my uppercase t. Again, whether you use uppercase t or lowercase t really doesn't matter. I'm just trying to differentiate the t's. And then, but this, the problem is right here, though. 1.3 are observed, right, which is not in the shaded region, right? So that means it's not critical. Okay, so this is not significant, not significant. If that's not significant, that means the equation is not going to be valid. It's not linear. It might not be anything at all. There might be no relationship. It might be some other relationship that's not linear, but we don't know at this point. All we know it's not linear. It might be something else. It's for a later chapter. Therefore, if I try to answer the question of 12 teachers, what's the ratio, I can't do it, because the model does not work because the correlation coefficient was not good enough. And if I remember correctly, it was like, oh yeah, it was 0.44. It was really bad, wasn't it? So therefore, we proved it doing a t-test that it wasn't actually good enough.